Dr. Sonam Khera, Madam, Assistant Professor at JC Bose, University of Science and Technology, for graciously accepting to guide today's session. A special warm welcome to our expert speaker, Dr. Arvind Kumarji, Professor J.S. Bose, University of Science and Technology, who will be sharing his valuable knowledge and insights on the crucial subject of energy conservation in thermal systems. This subject is of great significance in today's energy conscious world. And the theme today, it resonates deeply with global and national goals of sustainability and climate action. With energy being the backbone of the industrial growth and thermal system accounting for major share of energy consumption, conservation and efficiency, they are no longer options, but they are the necessity of today. And it is a role for the mechanical engineers. It is very vital, and we have to innovate, we have to optimize, we have to implement solutions that can reduce energy footprints while enhancing the productivity. We have participants across the country joining us today. It reflects the relevance of this subject and commitment of engineers towards building the sustainable future. I once again welcome all of you and wish this webinar to be enlightening, interactive, and impactful session. May the discussions today inspire us to adopt newer technologies and collaborative approaches in the field of energy conservation. With these words, I extend my best wishes for the success of this program. Thank you very much, ma'am.
Thank you, sir, for the warm welcome. Next, we are privileged to have with us Engineer Sajjan Singh Yadav, FIE Chairman of the Mechanical Engineering Division Board, IEI Kolkata, to address the August gathering. Before I invite him, may I take the privilege of introducing him to you all. Engineer Sajjan Singh Yadav, born in Rewari, Haryana, is a mechanical engineer with 37 years of experience in design, manufacturing, developing hybrid machines, automation, retrofitting, and warehouse management. He completed his BE in Mechanical Engineering from Engineering College Kota and BSc from Maharaja College, Jaipur. He worked with Orient Abrasive Limited and National Engineering Industries Limited before founding his own company, Sajjan Engineering and Consultancy Services, in 2017. His company specializes in automation, heat exchangers, tooling items, and machine upgradation in various industries. Engineer Yadav is actively involved in professional organizations including IEI, where he has held various leadership roles such as chairman of the Rajasthan State Center and National Council member. He has organized numerous seminars, workshops, and social projects, including COVID relief efforts. He is also a founder member and secretary of ECK Alumni Welfare Society, a member of Lions Club, and IIMM Jaipur. Currently, he serves as chairman of Mechanical Division Board of IEI headquarters and is also council member from Rajasthan State. I now invite Engineer Sajjan Singh Yadav to share his thoughts and insights with us. Over to you, sir.
Thank you, ma'am. Thank you very much. Distinguished panelist of the session, Dr. Arvind Kumar, moderator of the session, Dr. Sonam Khera, Engineer Inderjeet Singh Oberoi, Chairman, Faridabad Local Center, Institution of Engineers, India, Professor Pradeep Kumar, Honorary Secretary, Faridabad Local Center, Institution of Engineers, India, participant in this virtual session. Good evening to all of you. I welcome you all to the IEI technical webinar on energy conservation in thermal system, being organized by the Faridabad Local Center of the institution under the aegis of the Mechanical Engineering Division Board of the Institution of Engineers, India. Established in the year 1920 with its headquarters at Kolkata, the Institution of Engineers, India was incorporated in the Royal Charter on September 9, 1935, and the name of the century-old institution has been glorified over the decades as the only professional body in India to be accorded this honor. Since inception, this esteemed institution has upheld the mandate of promoting and augmenting the science, practice, and business of engineering through a variety of activities that provides meaningful insights to the policymakers regarding the matters related to the engineering profession. Moreover, the institution is mandated to operate all its functions as per the Royal Charter, bylaws, regulation, and code of ethics. The efforts of the Institution of Engineers India has always been to keep its members informed and abreast about the latest engineering and technological developments occurring in national and international arena through organizing technical events on regular basis involving eminent professionals and practitioners. Over its last 100 years of existence, the institution has provided valuable suggestions and policy inputs to the policymakers, contributing to the national growth. In addition to the regular technical events, technical webinars are being conducted by the institution on contemporary topics regularly, which provide a vital virtual knowledge sharing platform for our members and many other professionals attached to the trade. The webinar provided comprehensive coverage of various engineering topics, which have witnessed enthusiastic participation from a wide range of professionals. Thermal energy constitutes a significant portion of total energy consumption at enterprises level. The associated steam systems and heat exchangers conveying the heat generated from sources to the usage point also form an integral part of manufacturing process and service activities. However, the use of fossil fuels as a major source of primary energy for industry leads to environmental issues like pollution, climate change, etc. Those resources are non-renewable and will be depleted in the foreseeable future. This calls the immediate attention and action. Achieving energy efficient thermal system and processes with optimized design is a goal for researchers and engineers in view of rising energy costs and decreasing targets for greenhouse gas emissions. Energy efficiency is also vital if organizations remain competitive. Consequently, great efforts is being expended on enhancing both systems and individual components, because ultimately such enhancement leads to reduction in energy consumption cost and the impact of the systems on environment. I am confident that the technical deliberation during this virtual session will enrich the professionals' capabilities and strengthen the knowledge base of the working professionals, practicing, and young engineers. I wish the technical webinar a grand success. Thank you. Thank you very much. Jai Hind, Jai Bharat.
Thank you, sir, for sharing such insightful perspective on the subject. Now we are honored to have with us distinguished expert who will be sharing his perspective and research findings. His work not only contributes to academia, but also he has practical relevance for industry and society. Before we begin, I would like to introduce our esteemed panelist for today's session. Our panelist today is Dr. Arvind Kumar, Professor and Chairperson of the Department of Mechanical Engineering at J.C. Bose University of Science and Technology, YMCA, Faridabad. Sir brings with him an exceptional blend of academic excellence, research leadership, and administrative experience. He has served in multiple senior roles, including Dean of Interdisciplinary Studies, Dean of Management Studies, and Chairman of the Center for Energy Studies. His academic journey is marked by prestigious credential, PhD from IIT Delhi in CFD modeling for hydraulic and pneumatic conveying through pipeline, MTech from IIT Delhi in Energy Studies, and BTech in Mechanical Engineering from Aligarh Muslim University. Dr. Kumar research spans computational fluid dynamics, multi-phase flows, thermal engineering, refrigeration and air conditioning, fluid flow and energy conservation and management. He has guided PhD scholars and MTech dissertation, authored a book on energy management, and has published more than 80 research papers in reputed international and national forums. He is also actively involved with national academic bodies, serving as a member of NAC UGC inspection teams and committee member of DRC of several universities. He has chaired numerous technical sessions, delivered lectures in more than 30 national and international conferences, and contributed extensively to consultancy and research projects. Sir is a fellow of Institute of Engineers and life member of several professional societies. Dr. Kumar continues to inspire through his contributions to energy efficiency and sustainable technologies. We are truly privileged to have him with us today. Without further delay, I invite Dr. Arvind Kumar sir to deliver his expert talk on energy conservation in thermal systems. Over to you, sir.
Thank you, ma'am. Good afternoon to all. Good afternoon to Engineer Inderdeep Singh ji, Engineer Sajjan Singh Yadav ji, Dr. Pradeep Dimri ji, and participant of this webinar. It is a great privilege me to exhibit my views on conservation of thermal energy system. So I share my PPT.
Yes, sir, you can share. Dr. Sonam can stop her sharing and then you can share.
Yes, sir.
So energy conservation or basically the world is under the crisis of energy usage. So to put our pace of development with the sustainable world, we have to go for the energy use patterns, and sustainability depends upon the energy efficiency and energy conservation in each and every area of the life. And a major part of the energy consumed by our industrial sectors, and the major part of that, it is the thermal energy. In nature, so it's okay. Screen is visible now.
Yes, it is visible. Please, you can
Yes,
put it
sir.
on the full screen mode. Yeah. Yeah, perfectly all right.
Yeah, thank you. So energy conservation is the practice of reducing consumption by using less energy for the same level of output through efficient use of energy, our behavioral change, and the newer technology that saving the energy. Global energy, if we see that we are consuming oil 31%, it is the largest energy source used mainly in industry. Second major source is the coal. Third one is the natural gas, 23%, and it is used for heating, power, automobiles. Renewables, that is 13%, and it is the fastest growing sector. Solar, bioenergy, and nuclear is only 6%. So major source is the oil, coal, and natural gas. All are related in the energy that comes out in the thermal form. In Indian perspective, India having the 40% energy consumed from the coal. In oil, it is 24%, and it is used majorly in transport and industries. Natural gas, 12%, mainly used in fertilizers and industries. Renewable, we are much ahead average from the world. It is around 21%, fast growing sector, solar, wind, hydro, and nuclear. We are very little bit, 3%. And India is the third largest energy consumer in the world. So we are very much dependent upon the import. So our import bill is very much high on use of energy, and that is primarily thermal energy. The objective of energy conservation, that is a reduce energy consumption, improve efficiency of systems and equipments, ensure energy security and reliability, increase equipment's life and productivity, comply with energy and environmental regulations, create awareness and behavioral change, that we are supposed to go for the energy neutral, carbon neutral production or carbon neutral society. So it is very much depend about energy consumption and energy efficiency pattern. The common thermal systems are the boilers that use mainly in producing steams for power generation and for creating the hot water by burning the fuels. The furnaces that generate heat for melting, heating, or chemical process. Heat exchangers transfer heat between two fluids without mixing. Steam systems, that steam is distributed, different patterns, uses in power sector and for industrial usage in heating. Steam turbines that convert steam or thermal energy into mechanical work and consequently electrical energy. And a major energy consumed by our refrigeration systems, that is the chillers. So removing heat for cooling applications, cooling towers. So all are depend the energy consumption and improving the working efficiency of the system is save the energy. The operating principle of thermal system, every operating of principal system is energy conversion. The chemical energy combined in the fuel, it may be the oil, it may be the gas, it may be the coal, that convert in the combustion process into heat, and that heat energy used to generate the steam or flue gases, and that is used for different processes. And that all depend upon the heat transfer. Transfer of heat occurs by conduction, convection, and radiation, that is a different process. There are different methods of transferring the heat energy from one place to the other. And working fluids, that is the water that convert into steam and air or different gases that carry heat from one portion, one area to the another, or the one process to be the other process. Heat exchangers, expansion and work. The heat energy that having the steam, high pressure steam that expanded in turbine, in steam turbine, through the nozzles and moving blades that give the torque and ultimate run the alternator generator to produce the electrical power. And after that, the steam go into the condenser, and in condensation, that steam is condensed and back into the water that is feed to be the boiler again. And in the condensation process, that we go for the minimization of the loss by using the steam the heat into different processes, and efficiency optimization. Efficiency optimization, we are using the insulation, different controls, and maintenance and feedback system, so that our the losses should be the minimum, and if there is any problem in the system, in the maintenance area, we can visualize and taking corrective action timely. Major industrial application of thermal system, that power generation, that in steam turbine, boilers in thermal and nuclear power plants, iron and steel industry, furnaces for smelting, rolling and heat treatment, cement industries, kilns and heat exchangers for clinker production, petrochemicals and refineries, boilers, heaters, heat exchanger for distillation and processing. And textile industry, steam for dyeing, drying and fabric processing. Food and beverage industries, heating, drying, sterilization and refrigeration. Paper and pulp industry, steam for pulping, drying and chemical recovery. Pharmaceutical industry, controlled heating, sterilizing, drying. And HVAC system, that is building commercial boilers, chillers, refrigeration, cooling towers. If we are having the steam access, we go for the vapor absorption system rather than the vapor compression refrigeration system. Sectoral share of final energy consumption in India, the 40% energy consumed by the industry, 6% in agriculture, 8% commercial, 12% transport, and 24% residential. So residential is major energy consumed in the refrigeration, and in industry, a lot of energy is thermal sector. So how we have to improve the energy consumption and energy efficiency, so that in boiler, the proper combustion control, maintain correct air-fuel ratio to avoid incomplete combustion. So if there is any CO present in the exhaust gases, that will detect timely, and properly we have to maintain the proper airflow for the combustion air-fuel ratio. Regular maintenance, clean suits, scale and deposits to reduce heat losses. Insulation and leakage prevention, minimize heat losses from boilers, surfaces, steam pipes and valves. Feed water preheating, use economizer or waste heat recovery to preheat feed waters. A lot of energy is wasted in the blowdown. So blowdown control should supposed to be optimized, that reduce the heat and water loss. Condensate recovery, reuse condensate to save heat and water. Use of advanced control, install automatic control, oxygen CO2 monitoring system. Upgrading equipments, replace old boilers with high efficiency or fluidized beds boilers. So preheat combustion air with waste heat at every 22 degrees Celsius reduction in flue gas temperature, that increase boiler efficiency by 1%. If we use the air preheater, and air preheater preheat the air that is feed to be the furnace, air to the furnace, and if we increase the temperature 22 degree or 40 multiple of that one, so 1 to 2% energy is saved. So how much efficient system we have to take in the air preheater, that will reflected over here. Monitor residual oxygen in flue gas with flue gas analyzer at every 1% reduction in it, increase boiler efficiency by 1%. If there is a 1% oxygen reduction in flue gases, that increase the boiler efficiency 1%. Inspect for scale and sediments on the water side, as every 1 millimeter thick scale or deposit on water side that increases fuel consumption by 5%. Soot. Inspect for soot, fly ash, and slag on fire side, as every 3 millimeter thick soot deposit on heat transfer surface increases fuel consumption by 2.5%. Consider multiple or modular boiler units instead of one or two large boilers. If we take in the one large boiler, then the part loads, its efficiency is very less and losses are very high. So we have to take in the modular boiler on a smaller size, and on part load we can use in as per the need. In different boilers we can use. Provide automatic boiler blowdowns, and if already provided, monitor and optimize it. Recover boiler blowdown heat. Develop standard operating procedure for the same for the boiler. So every time the things that happen with the proper protocol, and the feedback is taken the timely and recorded. There is thermal energy flow in boilers. The energy that taken in the term of the coal or oil or gas, and it combust with the air. That output is the steam, and flue gas. And flue gas have the dry flue gas H2 losses that in the form of water vapors, and moisture in air, and CO losses, carbon monoxide. So that it should supposed to be the CO should not supposed to be the present, but there some little bit CO is present in the exhaust gases because of less time to in the combustion process. So that we add some excess oxygen, so that CO should supposed to be the nil or suppressed. And fly ash losses and bottom ash losses, the ash having two one, the clinker form, it is the bottom ash, and the fly ash, that is the suspended particulate matters, that is go with the exhaust gases, and that also contain the heat, and that is problematic for the environment. And the residual losses of the blowdown losses, that the sediments that is deposited continuously in the bottom, and we have to force to blow down in periodical manners. So the water treatment in that regard is very important. The quality of the water. So that is a pattern of different type of losses that occur in a boiler. Heat losses in flue gas is around 18%. Radiation and convection losses 4%. Energy output for boiler thermal efficiency, that 75 to 77%. And heat losses in blowdown is 3%. And we can improve the boiler efficiency through the with the high pressure boilers, that is supercritical or ultra supercritical boilers. So that efficiency is improved a lot. So now in the furnace thermal energy system, in the furnace optimization, furnace is in the furnace proper combustion control, and proper combustion control done with the help of maintain correct air fuel ratio to minimize excess air and unburned fuel losses, so that our new technology system, so that it can be managed well, correct air fuel ratio, so that our unburned fuel losses is supposed to be minimized. Temperature control, avoid overheating, operated at optimum furnace temperature for the processes. Heat recovery, use of recuperator, regenerators, or heat wheels to recover flue gas heat to further in the system. Minimize heat loss in the furnace, that improve insulation, seal leakages, and reduce opening times. That is, opening times of the doors, charging lids for any process in batch size furnaces. Efficient charging and loading, preheat charge materials, and optimize batch size for uniform heating. The charge should supposed to be the first it preheated, then before it put into the furnace, and the batch size should supposed to be the optimum. So the overheating or underheating in charge remains, and that leads to be the wastage of heat. Regular maintenance, remove scale, slags, clean burners, and maintain refractory lining, regular time interval. Automation and monitoring, use sensors and controls for temperatures, oxygen, and pressure regulations. So that is the typical energy flow in furnace. The energy in gross flow fuel input, so net fuel available, and a lot of energy waste in the flue gases, flue losses, and some energy loss in the wall, some remains there in furnace, and useful throughput, useful output is to be the energy in the material itself that heat the load, and some energy wasted in the cooling the furnace to proper functioning. So a lot of energy wastage in furnace itself. So that energy we have utilized in different process. The flue gases, the heat recovery from the flue gases, heat recovery from the cooling water, hot waters, and the minimum heat supposed to be stored in the furnace. Furnace is designed, or the placing of the load in the furnace so that the energy is maximum energy is supposed to be the utilized. So it depends upon the design of the furnace. The furnace or heat storage in the furnace structure, losses from the furnace outside walls or structures, heat transported out of the furnace by the load conveyors, fixtures, trays, radiation losses from openings, hot exposed parts, etc. Heat carried away by the cold air infiltration into the furnace, heat carried away by the excess air used in the burners. So energy saving potential in the furnace, we have to suppose to check against infiltration of air, use doors or air curtains, monitor oxygen, carbon dioxide, carbon monoxide levels, and control excess air to the optimum level, develop standard operating procedure for the monitor oxygen, carbon dioxide, all such type of data is taken timely and regular interval. Use ceramic fibers in the case of batch operations. Match the load of furnace capacity and develop SOP for the same. Retrofit with the heat recovery devices. Investigate cycle times and optimize the same, and develop the standard procedure for the same. So energy saving potential in furnace is very wide. Insulation refractory improvements 20%, waste heat recovery, recuperators, regenerators 18%, burner and combustion tuning 15%, furnace atmosphere control, oxygen fuel ratio that reduce the energy consumption up to the 12%, process optimization scheduling 10%. So that is a different energy saving potential in furnace, where the fuel, the internal energy of the fuel converted into heat energy, and heat energy into the useful energy. In that transit, that energy losses to be minimized. Now, third one is the steam system efficiency, steam distribution. The minimize leaks in the energy distribution network, and steam pipes should be insulated and maintain proper pressure across the length of the pipeline, steam pipeline. Condensate recovery, return condensate to the boiler to save fuels, water, and chemicals. And we should provide the regular intervals to be the where we can trap the condensate. Trap management, regularly inspect and maintain steam traps to avoid the losses in steam. Pressure and temperature control, match steam supply to actual process needs. Avoid excess pressure. So steam supply the pressure losses across the pipeline. So we have to maintain the flow of the steam across the length of the pipe in such a way that whatever we require the pressure, that pressure is supposed to be available, not much more, not less. So the proper matching of the pressure at different location of the pipeline is very necessary. And if there are variation, then we go for the condensation or different types of losses. And similarly, we have to avoid excess pressure. Waste heat recovery, use economizers, heat exchangers, and flash steam recovery. Efficient and use energy efficient equipments, heat exchangers, rats, and the turbines. Fix steam leaks and condensate leaks. As every 3 mm diameter hole on pipeline carrying 7 kg per centimeter square, 7 kg per centimeter square steam waste or 33 kiloliters of fuel per year. If any steam in pipeline that have pressure of 7 kg per centimeter square and there is 3 mm hole, that hole tends to waste of the energy 33 kiloliters of fuel per year. Ensure condensate is returned to and reused in the process, as every 6 degrees centigrade raise in feed water temperature by economizer condensate recovery results in 1% saving fuel consumption in boiler. Remove air from in direct steam using equipment, as every 0.25 mm thick air film offers same resistance to heat transfer as 330 mm thick copper valve. So air is if there is any air trapped, so that it provides the high resistance, so that hinders the transfer of heat, and that leads to a very high energy loss and overheating of the system. So it reduces the life of the plants, life of this line, and as well as the reduce the energy use or power generation So that is the energy saving in steam using equipments. If we take in that boilers and boiler have checked valve whether steam valves are open or closed when equipment is used or not. Pressure reducing valves connected with the separators, and we are in the separator we confirm the we have to use the dry steam, not the wet, and further control steam to the optimal pressure for the product being heated in the process industry, and properly insulated equipments, and that completely remove condensate and air from the equipments. Basically, air present in the steam if adversely affect the condenser efficiency, and further the recover and reuse of the condensate. Then the condensate come to the feed water tank, and it is a system that is supposed to be the follow in the process steam in the process industry. Turbine heat rate and efficiency, steam pressure and temperature. In turbines, steam pressure should supposed to be the higher side, and we are going for the supercritical boilers where the very high steam, that pressure have more than 273 bar. So the efficiency of the steam turbine is very high. At higher the pressure, more the efficiency. And quality of steam, the subcritical steam turbine very much depends upon the quality of steam. If steam is bad, the efficiency of steam turbine reduce drastically. So we have to maintain proper dryness, and the steam have some superheat. And within the turbine, steam remains in expansion mode, the dry. So we have to sufficient superheat and in the expansion process till the steam comes out. Blade design and conditions, the steam blades should having the high temperature strength, so the erosion is not be occur at high elevated temperature in longer periods. And fouling reduce the erosion and fouling reduce efficiency adversely if the blade is eroded or there any fouling occur. So that very much depends upon the steam conditions. Load factor, and at the part load efficiency decrease very much. So we are using the steam turbine at a proper load, and we have to design the system such a way that we are operating turbine at continuous load, and we have to adjust the load after that. And maintenance of seals, bearings, and nozzles that also affect the turbine efficiency. So in steam turbine, we are supposed to be reheat and regenerative cycle. Reheat cycle give the superheating across the steam turbine, and regeneration improve the efficiency, thermal efficiency of the steam turbine. Proper maintenance of blades and seals, that is very much necessary. Operate at optimal load conditions. Upgrade controls for better steam flow regulations, that is steam turbine 30 to 45% efficiency, and overall plant efficiency 35 to 40%. Gas turbines 25 to 35%. in open cycle and in closed cycle coupled with the steam turbine, that up to 55 to 60% in combined heat and power generation, or that is with cogeneration, gas turbine co-generated with the steam turbine. So that is the turbine heat rate and efficiency. We see that is the graph, thermal efficiency and heat rate. So if we increase the heat rate, the thermal efficiency improve, and if we the heat rate is decreases, thermal efficiency improve, and if heat rate is increases, thermal efficiency decreases. So we have to maintain a proper heat rate for the steam turbine, so we get the optimum condition for the running of steam turbine. Cogeneration. Cogeneration is a simultaneous production of electricity and useful heat from the same fuel source, coal, gas, biomass. We have to generate the high pressure steam, that is first used in the steam turbine, and the exhaust of the steam turbine not go for the condensate, it go for the industrial processes, and where the heat energy of the steam is utilized, then condensate, then that condensate go for the again in boiler. So such type of process is called the cogeneration, that improve. Unlike conventional power plants, combined heat and power utilize the heat of industrial processes, heating or cooling. We go for the cooling in vapor absorption refrigerant system or steam refrigeration system. If we are having that one, so we go for the cooling system, that is very around a lot of energy used in the household or the commercial buildings, that can be utilized. Conventional power plant efficiency 30 to 40%, and cogeneration we go to around 70%. 70 to 85% as waste heat is utilized CHP system. Topping cycle, electricity generated first and waste heat used for the heating. Bottoming cycle, heat used in the process first, waste heat drive a turbine for power generation. So in industrial process, or we say in the that can use in bottoming cycle in industry, just like steel making process, where the furnaces have very high temperature. So first and the heat is used for the process of melting, then the waste heat is used for the steam generation and run the turbines. Waste heat recovery system, that economizers are used in boilers, that for feed water, and air preheaters, recuperators, regenerators, that recover furnace heat, heat exchangers, everywhere heat exchanger used in different forms. Waste heat boilers generate steam from exhaust gases that comes out from the melting of the steel, melting of the different metals. Waste heat boilers generate steam from exhaust gases. Organic Rankine cycle turbines generate electricity from low-grade heat, that bottoming cycle for the steam turbines. Improve overall plant efficiency, that is 10 to 30%, and that used in the cement industry, steel industry, glass industry, chemicals, refineries, and different power plants. Waste heat recovery, recover heat from flue gases, engine cooling waters, engine exhaust, low pressure waste steam, drying oven exhaust, boiler blowdown, etc. Recover heat from incinerator of gases, utilize waste heat for applications like fuel oil heating, boiler feed water heating, outside air heating. Use chiller waste heat to preheat hot boilers, water. Use heat pumps rather than we direct use the electric energy for heating anything. Use absorption refrigeration in comparison to the vapor compression refrigeration system, where we can use the waste heat or waste heat of the steam. Use thermal wheels, run around system, heat pipe systems, and air to air heat exchangers. That is the working of wheel heat recovery unit. So we can get using the recovery wheel in recovery of the heat energy or minimizing the cooling load in HVAC system. Insulation, and insulation also having the big role in reduction of heat losses in the industry, in the furnaces, in boilers. Prevent heat losses from boilers, furnaces, steam pipes, equipment surfaces that are the mineral wools, glass wools, ceramic fibers, calcium silicate, boards. And they have so many benefits. It reduces surface heat losses, improve process temperature control, enhance personal safety, and it saves 5 to 15% fuel energy. And we are optimize the economic thickness of insulation. More the insulation thickness, minimum the steam and energy loss, but it increase the cost. So the optimum thickness we have to consider with the factor of cost. The optimum cost of insulation. Repair damaged insulation. Remember thumb rule: a bare steam pipe of 150 mm diameter and 100 meters length, carrying saturated steam at 8 kg per centimeter square, would waste 25,000 liters of furnace oil fuel in a year. Insulate open tanks. Remember the thumb rule: 70% heat losses can be reduced by floating a layer of 45 mm diameter polypropylene balsams the surface of 90° centigrade hot liquid condensate. That is a major factor we can go if it is not used by, so it's supposed to be the use by the industry. Steam pipeline, it have potential of saving 25%, boiler and furnace 20%, hot water system 15%, heat exchanger and tanks 12%. Refractory, high temperature resistance materials. It protects furnace, boiler walls, lining, and vessels exposed to the extreme temperature. It has fire clay, high alumina bricks, silica, magnesite, castable ceramic fibers. It reduces the fuel consumption and heat losses. It improves the life of equipments. It improves the efficiency and lower the operating cost. Furnace and walls roofs, it reduces the 22%, doors and openings 18%, burners and block. That different area have such type of potential of saving the energy. Efficient heat exchangers. Efficient heat exchangers offer significant energy savings by recovering and reusing waste heat that would otherwise be lost to the environment. Modern designs, enhanced materials, and smart operational strategies can improve energy efficiency by 30% or more, resulting in lower operating costs, reduced emissions, and smaller carbon footprints. Use compact designs of heat exchangers, ensure clean surfaces, optimize flow arrangements, apply enhanced surfaces, maintain correct temperature, high heat recovery and energy efficiency. Process integration with pinch analysis. Pinch analysis is systematic techniques for analyzing heat flow through the industrial processes and is based on fundamental thermodynamics principles. The pinch method readily identifies opportunity in complex heat exchanger networks. Pinch analysis generates targets for heat recovery. It provides a conventional way of qualifying how close any given design option is to the optimum. A pinch occurs where the vertical distance between the hot and cold composite curves equal, where the temperature difference is minimum. So that is a graphical representation of the pinch, and there are two streams in flowing. One stream flowing from I to this one, and another stream flowing the reverse side, and the temperature difference in these two, in that area where the delta T is the minimum. So that is the pinch, and this area is called the below pinch, and that area is called the above pinch. And hot utility targets, steam furnaces, and cold utility targets, air cooling, refrigeration. So opportunity for process heat integration. So that integrate the heat energy with the process, so that our heat exchanger have supposed to be the optimum design. We get it if we get the pinch point. Now, for the saving, we are supposed to be the renewable integration and hybrid system. Hybrid system is more efficient than any individual system in isolation. Automation and controls. Automation is use of technology to operate processes system with minimal or no human intervention. And controls are the method system used to regulate and the machines. And it's applied in robotics, manufacturing in robotics, power plants, process industries, building automation. And life cycle cost analysis for the now the different government policies, now energy efficiency, conservation and sustainability, and zero carbon. So that different mechanisms that promote the energy conservation activities across the industries. The carbon trading or carbon tax. So the National Energy Conservation Act 2001, energy efficiency missions, renewable energy policy, solar, industrial energy efficiency programs that also promote energy conservation in thermal system, that give you the incentives to enhance the or optimize the system or newer technology. ISO 5001 energy management system global standards. Supercritical, the emerging technology in energy conservation, supercritical and ultra supercritical boilers. So that operation of that boilers are typical, but it gives the efficiency in very large, more than 60%. So now newer regulation of government is that we are supposed to go for this type of thermal power plants that operated the supercritical and the supercritical boilers or cycle. You go for that one. Advanced gas and steam turbines. And gas turbines should every time should support coupled to be the steam turbines. We have to go for the industrial best practice in the energy management system, cogeneration, benchmarking, and energy audits, building sectors, green building codes, and roadmap for thermal energy consumption in Indian industry, 1 to 3 years energy audits and benchmarking, low cost efficiency measures, insulation and heat recovery, trainings, adoption of standards, technology modernization, cogeneration, and we go for the tri-generation. Digitalization of smart controls we use for the AI and Internet of Things, predictive maintenance, continuous optimization, digital twins, roadmap, renewable energy integration, decarbonization pathway, gradual shift towards electrification of thermal processes, adaptation of green hydrogen and carbon capture technology, financial supports, that market-based instrument for these technologies to implement. So that is a major conservation measures, boiler efficiency, furnace optimization, steam system efficiency, turbines with cogeneration, insulation refractories, efficient heat exchanger, waste heat recovery system, renewable integration, digital monitoring, training, and capacity building. Resource efficiency, cost saving, environmental protection, policy compliances, future competitiveness. So, in the conclusion form, thermal system from the backbone of industrial energy use, but they are also major contributors of fuel consumption and greenhouse gas emissions. Energy conservation in this system is therefore not just an economic necessity, but also an environmental responsibility. Thank you, sir. Thank you for patience listening.
Thank you so much, sir, for sharing such valuable insights on the subject. Your perspectives add in significant depth to the discussion. Thank you so much, sir. Now, participants are requested to type their queries in the chat box or raise their virtual hands.
I think Dr. Sonam, they have written some questions,
Yes,
so we can
right,
take.
sir. Right, sir.
Can take some questions we can take.
Yes, one of the participant has written, what is the importance of energy conservation in the thermal systems?
I think it has been celebrated.
It is a very significant aspect that energy consumption in thermal system. Basically, 40% energy consumed in industry, and the major part, around 60% in thermal one. So if we go for incremental energy consumption, that in terms of the insulation, in terms of the process improvement, in terms of the pinch analysis and economizers, so heat exchanger, and that is economizing part of that one. So where we have to improve in terms of the monitoring process, in terms of the process, in terms of the combustion analysis. So all that reduce the burden of CO2 emissions, and it also cost effectiveness of the industry of any, ultimately come on the product. Basically, if you are not energy carbon neutral, so carbon tax is imposed on the product that is bear by the industry itself. If you reduce the energy consumption in any process, that you that is benefited in so many ways.
Okay, thank you, sir. Next question is, what do you mean by supercritical thermal power plants and role of thermal systems?
Basically, super thermal power plant having the steam having more than pressure above the critical pressure, that is at 225 bar. When the steam having more than 225 bar pressure, so that time steam having the gaseous and liquid both characteristics simultaneously. So in the gaseous form, heat transfer is less, and liquid form is gas transfer. The heat transfer is very high. Okay, so the conversion of absorption heat from the flue gases in supercritical form is very high, rather than the steam form, gaseous form. The absorption heat in the gaseous form is less, but in liquid form, it's very high. So the absorption of heat is very high. Okay, so we required a very little space, less space than the conventional subcritical boiler. They are having very high pressure, but less volume. So the volume is reduced of the boilers. So the size of the any steam power plant is reduced, and it improves the heat transfer rate. So it ultimately enhances the improvement of the efficiency of the steam power plant.
Okay, thank you, sir. And next question is, one more participant has asked, how much we have the technology to make it happen?
Which one? Supercritical boiler.
Right, sir.
In supercritical boiler, we are having the basically boilers are available, but problem with the turbines. They are having run by very high pressure on high temperature in long run. So the turbine blades are eroded once it continues very high pressure around 600 above the 600 degree centigrade. The blade is eroded very fastly. So now the newer technology, the blade is the ceramic coating done on the blades. So that such type of blades now available. That is a costly process, but now such type of things are available. The turbines are available, and they are installed across the globe. And India is also one. It's 600 megawatt super thermal critical power plants in under operation. So that thing is implemented, but it is a problem to be the cost wise.
Sir, one more question from a participant, Pankaj Kumar. He has written one thing. How environmental engineer can contribute, they required in the process? Are they required in in this process?
The environmental engineer having a great role in the zero carbon zero carbon emissions, zero carbon neutral industry. Whatever the carbon emitted, so that how that emissions can be, CO2 emissions are there, how that CO2 emissions are minimized or compensated with the different processes by saving the energy or by using the basically that offsetting by planting the tree, planting the forest. So environmental engineer is to be estimate how much energy, how much emissions are there in terms of the CO2, and how that CO2 compensated with the forest or with some other processes.
There is one more question from Dikshit Kumar. Is there any online digital platform to measure and analyze the outcome of energy conservation in electrical and mechanical utilities?
The board of BE site is there. They are having different tutorials available. Bureau of Energy Efficiency. So they can get from there.
Okay. Yes. Thank you, sir. And one more question from Shazan K. Thomas. How strong is India in steam turbine design? And any challenges faced in advanced material technology?
Basically, that is in India, we are in the R&D phase. Basically, we are not commercialized that technology. We are the R&D phase, but in across the globe, they are commercialize it.
Okay, sir. And one more question is there, sir, from anonymous attendee. How do the first and second laws of thermodynamics influence the efficiency and energy conservation of the thermal systems?
Basically, first law of energy conservation, energy neither created that used in the combustion process. ठीक है ना? तो combustion जो process है, that is governed with the first law of energy. And how it is utilized, the second law of thermodynamics, that is there. The second law of thermodynamics never be heat energy never be converted into the equal amount of work. So how the heat energy optimize use? So that we never go the high grade energy to be the lower grade energy, but lower grade energy utilized in different proportion, different activities. So that manner we can be go. And one thing is there, exergy analysis are there. The where there's a high grade in the higher the temperature side, more the available energy. The lower the temperature side, the less available energy. So that the quality of energy depends upon the temperature.
Thank you, sir. And there is one more question from Swapnil. Is there any innovative or cost-effective refractory material available for kiln used for iron generation other than mullite-based refractory lining material?
Basically, refractory material depends upon the applications. We cannot say that one thing is utilized commonly everywhere. So that matrix depends upon the applications.
Okay. Thank you so much, sir, for the queries, answering the queries. Thank you so much, sir. To formally extend our gratitude, I now invite Professor Pradeep Kumar Dimri to deliver the vote of thanks. Before I invite him, may I take the privilege of introducing him to you all. Dr. Pradeep Kumar Dimri is a professor in Electronics Engineering Department and Dean of Student Welfare at JC Bose University of Science and Technology, YMCA, Faridabad. He is a fellow member of the Institution of Engineers and life member of the Indian Society of Technical Education. Currently, he is also serving as the Honorary Secretary of IEI Faridabad Local Center. Over to you, sir.
Thank you, Dr. Sonam. Good evening, all. Respected Chairman and Council Member IEI Faridabad Local Center, Engineer Inderdeep Singh Oberoi, Engineer Sajjan Singh Yadavji, Chairman Mechanical Engineering Division Board, IEI Kolkata, Dr. Kingsuk Sen, Assistant Director, Technical Department, IEI Headquarter, Kolkata, our expert speaker, Professor Arvind Kumar Gupta ji, Professor and Chairperson, Mechanical Engineering, JC Bose University of Science and Technology, YMCA Faridabad, my fellow FLCC committee members, and all the audience presents. Good evening. On behalf of the Institution of Engineers India Faridabad Local Center, this is my privilege to propose the vote of thanks to all those who have directly or indirectly contributed to this webinar on the topic of energy conservation in thermal system. I think this was a huge success. I would like to express my sincere gratitude to Engineer Sajjan Singh Yadavji, Chairman Mechanical Engineering Divisional Board, IEI Kolkata, Dr. Kingsuk Sen, and all and Mr. Sudeep Chakravarti for their and their team for their support in creating the facility to host this webinar. My sincere thanks to expert speaker, Professor Arvind Kumar Gupta, who has made an excellent presentation, and considering the number of questions we have got, I think there was a meaningful participations from the audience as well. My special thanks to event moderator Dr. Sonam Khera, Assistant Professor J.C. Bose, University of Science and Technology, YMCA Faridabad. She has been quite a good sport here and made a very good moderating in this session. Last but not the least, I thank our honorable II members and all the participants who have blessed this on this occasion and who have taken the valuable time out of their busy schedules. Your presence and participation has made this event up to mark. With these words, I would conclude, and with this, we conclude the webinar. Thank you. Jai Hind.
Thank you,
Jai
sir.
Hind.
I am from the
Thank you,
headquarters. Thank you, sir, for such a beautiful webinar. And I think it was very fruitful webinar because lots of participants were there and there are lots of questions. I may request the panelists sir may share his PPT because lots of participants are requested for these beautiful PPTs. So much informative PPT. So it may, if we can share this PPT to the participants, it will be helpful. And also thank to Faridabad Local Center for organizing such an event with such a contemporary topic. I hope some more beautiful topic and will come up in from Mechanical Engineering Division. Thank all of you, sir. With this, I am ending the webinar.
Thank you.
Thank you, everyone.
Thank you. Thank you, Pradeep ji.
Thank you, Ji. Thank you, sir.
Thank you.